In the intricate world of microchip manufacturing, one company holds an unparalleled position, ASML. This Dutch firm, headquartered in Veldhoven, isn't a household name, yet its machines are the very foundation upon which the digital age is built. Industry analysts consistently highlight ASML's near-total monopoly on extreme ultraviolet, or EUV, lithography. This isn't just a niche market. EUV technology is essential for producing the most advanced semiconductors, powering everything from your smartphone to cutting-edge AI. Without ASML's innovations, the leading edge of chip development would simply halt, a dependence that analysts describe as a global chokehold. ASML's journey began in 1984 as a joint venture between Philips and ASM International, born out of Philips' Semiconductor Equipment division. In its early days, the company faced stiff competition, particularly from Japanese giants like Nikon and Canon. However, a crucial strategic decision set ASML on its unique path, focusing on advanced, next-generation lithography systems, even when the underlying technology was nascent and unproven. While competitors refined existing deep ultraviolet, or DUV, methods, ASML embarked on a highly speculative, decades-long quest to develop a fundamentally new form of light for chip printing. This ambitious divergence laid the groundwork for its future dominance. The transition from DUV to EUV was not a straightforward evolution, but a monumental leap. The concept of using extremely short wavelength ultraviolet light, around 13.5 nanometers, offered the promise of printing far smaller features on silicon wafers. However, generating, controlling, and reflecting this light proved incredibly challenging. ASML, alongside a consortium of chipmakers like Intel, Samsung, and TSMC, poured billions into research and development. This collective industry investment, totaling over 20 years and an estimated 6 to 10 billion euros, was critical. No single company could have borne the cost and risk alone, establishing a unique collaborative ecosystem that ultimately cemented ASML's lead. One of EUV's most significant breakthroughs lies in its light source. Unlike DUV, which uses conventional lasers, EUV light is generated by a process known as tin droplet-fueled plasma. A high-powered CO2 laser fires precisely timed pulses at microscopic droplets of molten tin, causing them to vaporize and form a plasma that emits 13.5 nanometer light. This intricate dance occurs at an astonishing rate, sometimes 50,000 times per second, within a vacuum chamber. Experts describe this as a controlled microexplosion, a testament to the extreme engineering precision required. The complexity of this source alone created an immense barrier to entry for any potential competitor. Beyond the light source, handling EUV light presents another colossal challenge. Ordinary glass lenses absorb EUV light, making traditional optics useless. The solution, developed through a critical partnership with German optics firm Carl Zeiss SMT, involved creating highly precise multi-layer mirrors. These mirrors, made with alternating layers of molybdenum and silicon, are polished to near-atomic perfection and operate within an ultra-high vacuum environment to prevent absorption by air molecules. A single mirror can cost millions, and the EUV scanner uses multiple such mirrors, reflecting the light over several meters without significant loss, a feat of optical engineering previously thought impossible. ASML's competitive moat is fortified by thousands of patents and decades of accumulated expertise. The firm holds an estimated 80% of all patents related to EUV technology. This vast intellectual property portfolio, combined with the proprietary knowledge gained from countless engineering iterations, makes it virtually impossible for new entrants to catch up. Competitors like Canon and Nikon, who initially dominated DUV lithography, chose not to make the same multi-billion-dollar bet on EUV. This strategic divergence allowed ASML to establish an unassailable lead, ensuring that any company attempting to replicate ASML's capabilities would face not only immense R&D costs but also significant legal hurdles. Major chipmakers like TSMC, Samsung, and Intel are not just customers, they are critical partners and, by necessity, dependents. To produce the most advanced chips at 7 nanometers and below, EUV lithography is indispensable. Older DUV systems simply cannot achieve the required resolution and feature density economically. For instance, TSMC's ability to produce chips for Apple's latest iPhones relies entirely on ASML's EUV machines. Similarly, Samsung's foundry business and Intel's renewed push for process leadership hinge on access to ASML's cutting-edge technology. This dependency ensures a constant demand for ASML systems, despite their extraordinary cost, which can exceed $200 million per unit. The difference between EUV and its predecessor, deep ultraviolet (DUV) lithography, is stark, especially when it comes to feature resolution and manufacturing efficiency. DUV typically uses a wavelength of 193 nanometers and requires complex multi-patterning techniques to achieve smaller features, adding significant steps and cost. EUV's 13.5 nanometer wavelength allows for single-pass patterning, dramatically simplifying the manufacturing process for sub-7 nm nodes. This efficiency gain, coupled with superior resolution, makes EUV economically viable for advanced nodes where DUV would be prohibitively expensive and complex. This technological chasm is why leading foundries view EUV as an absolute necessity. ASML's monopoly has profound implications for the global semiconductor supply chain. It creates a single point of failure and, crucially, a point of geopolitical leverage. Governments, particularly the US, have increasingly pressured the Dutch government to restrict ASML's sales of advanced EUV machines to certain countries, notably China, citing national security concerns. This transforms ASML's technology from a purely commercial product into a strategic asset. The bottleneck created by ASML's unique position means that global access to cutting-edge chips is, to a significant extent, controlled from a small town in the Netherlands, impacting everything from economic competitiveness to military capabilities. ASML isn't resting on its laurels. The company is already developing the next generation of its technology, High-NA EUV. This innovation aims to further increase resolution and throughput, enabling even smaller features for future chip nodes, potentially 2 nanometers and beyond. While High-NA EUV presents its own set of formidable engineering challenges, including even larger and more complex optical systems, ASML's deep institutional knowledge and continued industry partnerships position it to maintain its dominance. The relentless march of Moore's law, the principle that the number of transistors on a microchip doubles roughly every 2 years, continues to be facilitated by ASML's singular vision and engineering prowess.